All right, here we go. So arc length. First of all, when we're thinking about arc length, let's just for a moment think about if we were going to find the length of an arc like this. Well, it's curved, right? So you can't use the distance formula straight up. But what if I found the distance between a bunch of points along here? So like if I found the distance from here to here and there to there, and just keep finding distances between different points along the curve. And what if I move those points closer and closer and closer and closer together and keep finding those distances and adding them all up? What does this kind of start to sound like? I'm adding up a bunch of stuff. Yeah, exactly, Noah. Starts sounding kind of like integration, right? And that's exactly what we're going to be kind of driving at here as we go through and derive this arc length formula. Okay, so since we're using the distance formula here, the arc length is going to be the limit as n goes to infinity of this summation of values from I equals 1 to n as we get more and more pieces that we're adding together of basically what the distance formula is. So the square root of x sub I minus x sub I minus 1 squared, so that's our change in x, plus y sub I minus y sub I minus 1 squared. So this is basically our distance formula here, the square root of the change in x squared minus the change in y, or plus the change in y squared. Okay. So we're going to take this and manipulate it a bit to make this into something that we could integrate. Okay, so for now, we're just kind of thinking distance formula. Okay, so then let's say we apply the mean value theorem here on the interval xi minus 1 to x sub I. Okay, so if we do that, what that tells us, because basically what we're going to do right now is try and figure out a way to write the y values in terms of x, basically. So what that tells us is that there exists some value c such that f of x sub I minus f of x sub I minus 1 is equal to f prime of c times x sub I minus x sub I minus 1. So the nice thing here is that this is the change in y, and this is the change in x. So if I replace it with those terms real quick, we get that the change in y is equal to f prime of c times the change in x for some value c. Okay. So then up here, we can kind of, in our distance formula, replace the change in y with this f prime c change in x. So we're starting to get things to be in terms of x like we want them to be. So the square root of the change in x squared plus the change in y squared is going to be equal to the square root of the change in x squared plus f prime of c change in x squared. Then, kind of further manipulating this, well, these both have a change in x squared in them, right? So if I factor out a change in x here, or even a change in x squared, we get that. And then thinking about kind of the ways that we can manipulate a square and a square root, we can take the square root of this x squared, so we just get 1 plus f prime of c squared times the change in x. Since we can have the square and the root cancel each other out. And this is starting to look more and more like integration here, right? Because change in x is just dx. So this is where we get if f prime is continuous on the interval a to b. The arc length, which is often done with an uppercase capital L, is equal to the integral from a to b, and this is the length of the arc from a to b, times the square root of 1 plus f prime of x squared dx. Or sometimes you'll see it written as the integral from a to b of the square root of 1 plus dy dx squared dx. So these are kind of the two formats that you'll see it written as, and these are the things that we need to remember. This is the big deal for today. Okay. So that's where we get the integral for arc length from. It's from the distance formula, and it's from figuring out how to put change in y in terms of change in x. And also, since we're applying mean value theorem, we do need that derivative to be continuous for this formula to work out. And that's not to say we can't take, or like if we end up with a derivative where we've got a problem where it's not continuous or it doesn't exist for a certain value within our limits, that we can't find other ways around that. But in general, you're going to need the derivative to be continuous on the interval. Okay. So now that we've figured out what the arc length formula is and everything, now we're going to apply it. and actually find some arc lengths here. And the finding of the arc lengths usually is a lot more simple than deriving the arc length formula. So here we go. Grab another piece of paper since I am running out. Okay, first example. I am walking along a path. Defined by y equals natural log of secant of x. And I'm walking along it from x equals 0 to x equals pi over 4. Because whenever I'm walking along a path, I have to define it mathematically first. That's how you go for walks, right? No? I'm the only one? Okay. So we're walking along this path, and we want to know how far did I walk? Okay. Well, first then we need to remind ourselves of our arc length formula. Okay. So we're reminding ourselves of our arc length formula there. And so the first thing we need to do is figure out the derivative, y prime, for natural log of secant of x. So the derivative of natural log is 1 over whatever is in here, and then we have to chain rule it. So we have 1 over secant of x, and then chain ruling the derivative of the inside secant is secant times tangent. But then we have a secant on top and a secant on the bottom, so we can cancel those out, and we are left with only tangent. And I'm going to go answer a question from Study Skills real quick. Okay. Good to go there. All right, so we're left with the derivative is just tangent of x. So then we have to plug that in here. And our bounds are from 0 to pi over 4. So the integral we're going to use 0 to pi over 4 of the square root of 1 plus tangent squared x dx. Okay. Anyone notice something convenient that happens here? Is there a trig identity we can use? Yeah. 1 plus tangent squared is secant squared. And then we can just end up with secant x dx. Okay, and then knowing our integrals here, integral of secant x is natural log of, I think it's secant plus tangent, right? Yeah. From 0 to pi over 4. And then we got to plug that in. So natural log of secant of pi over 4 plus tangent pi over 4 minus natural log of secant of 0 plus tangent of 0. And then secant of pi over 4 is the square root of 2. Tangent of pi over 4 is 1. Secant of 0 is 1. Tangent of 0 is 0. So then we get natural log of root 2 plus 1 minus natural log of 1. And the natural log of 1 is 0. Because log of any log of 1 is 0. So then we get, for our final answer, natural log of root 2 plus 1. And if this was a non-calculator question, this is probably about as far as we'd be expected to take it. If it was a calculator question, then obviously you toss it in your calculator long before this and get the answer as a decimal and move on with your life. But if this was a non-calculator question, this is about as far as we would take it. Okay. Any questions so far? And if you have a question, feel free to unmute and say so.
So the integral of like 1 plus tangent x, like tangent squared x, do we just like, since we know that secant x is equal to that because of the trig identity, would this be classified as a trig integral?
Probably not in the way that we dealt with trig integrals back in chapter 7. This would probably just more be, this would be an integral that you could be expected to do in AB. Yeah, with just being able to manipulate trigonometric functions like that with identities. Yeah, most of the trig integrals from chapter 7 were kind of the variety of like a trig function to a power times another trig function to a power, and figuring out how to creatively use substitute with those. But yeah. Okay. Any other questions, comments, concerns so far? Okay. So we're going to look at a couple of others, and the other ones that we're going to look at are ones that that we might run into that have an issue with the domain of the derivative, or an able to have the derivative at a certain value along the domain. So let's take a look at some of those and some creative ways that we can kind of circumvent a few things here. So the first one we're going to look at example number 2, we're going to do the length of y equals the cube root of x on the interval -8 to 8. Okay. So if we take the derivative here, we know that this is x to the 1/3 power, right? So then it would be for y prime 1/3 x to the -2/3, or 1/3 times x to the 2/3, which is probably an easier way to look at it and think about it when we see an issue here. Is there a value in our domain here that we're looking at that we can't take, or that the derivative doesn't exist at? For what value of x do we have a problem here? Anyone have an idea? Yeah, Kristen's got it, 0. That's a problem. Yeah, can't take the derivative at 0 here because you can't have a 0 in the denominator. And if you think about the way this function looks, we can kind of find a way to get around this. So let's draw that cube root. And when x is 8, the cube root of 8 is 2. When x is negative 8, cube root of negative 8 is negative 2. And we want to find this arc length, but we have an issue here with 0. So here's what I'm going to propose that we do. What if we instead looked at y equals x cubed? They're inverses. So this function is the same thing as this reflected over the line y equals x. And so because of that, a reflection is a rigid transformation, right? It doesn't change a shape, right? Remember from geometry, if you did a reflection, it doesn't change the shape at all. It doesn't change the size or anything like that. It's just positioned differently. Same thing goes for functions. So instead, if we took the inverse and wanted to find from where y is negative 8 to y is 8. So when y is 8, x is 2 for this one. When y is negative 8, x is negative 2. So we could instead find the arc length of this curve from negative 2 to 2, and it would be the same length. We just wouldn't have that issue where the derivative is discontinuous. Because the derivative, if y is x to the third, the derivative is then 3x squared. And we no longer have that issue of a discontinuous derivative. Okay. So this is just kind of a way to get around something. And this would typically be a calculator question if they ask you to actually calculate out this to however many decimal places, 3 for the AP test. So then our arc length, negative 2 to 2, square root of 1 plus 3x squared squared dx. And then on one like this, you can stick it into a calculator. You could simplify it a little bit further if you would like to before you stick it in, whatever makes it easier to, not accidentally forget parentheses and stuff like that. Since this one is symmetrical, you could also, since on this end from 0 to 2, it's going to have the same length as from negative 2 to 0. If you wanted to, you could go 2 times the integral from 0 to 2 of this and get 1 plus 9x to the 4th when you distribute the square here. But at this point, you would just be sticking it into a calculator anyway. So whatever step is easiest to stick it into the calculator at for you is fine. And we should get approximately 17.261. Okay. So that's one kind of different case that we might see. And a way that we can kind of get around that. Another case that we might see where we have a little bit of an issue sometimes is an absolute value. So we'll talk about that as well, what to do with the absolute value. But first, any questions with the second example? Any numbers we're not sure where they came from? Things we're not sure how they happened? Okay. Then let's do another. All right, for this one, we're going to go with find the length of, we'll go with is x squared minus 4 absolute value of x minus x from x equals -4 to x equals 4. Okay, and so when we look at the graph of this one, because this would also typically be a calculator question, we notice it looks something like that, where we end up with a cusp here, and that's a bit of an issue. So one way to kind of circumvent this is to split up the integral and go from -4 to 0 and 0 to 4, and based on where x is positive and negative, to deal with the absolute value. But that's kind of a pain. So there's something else that we can do here. And it has to do with the way that we write the absolute value of x. So another thing that we could do is we could take the absolute value of x and go, okay, well, the absolute value of x could also be written as the square root of x squared. Okay. So when we go to take the derivative of this thing, writing this as the square root of x squared helps us out here. And I'm going to write it actually as x squared to the 1/2 for the purpose of taking the derivative. Because then when we go to take the derivative, it's a little bit more simple to work with. So we get 2x, and then 4 times 1/2 is 2. And then we still have x squared inside, and it's going to be to the -1/2. And then chain rule, we have to take the derivative of the inside, so times 2x. And then minus x just turns into -1. And then we'll clean this up a little bit. So we have 2x, and then in here we have 2 times 2 is 4. And then x over square root of x squared minus 1. And now that we've gone through the process of taking the derivative and everything, we can turn this back into the absolute value of x. Okay. So then this is what we're going to plug into our arc length formula. All right. And at this point, I would toss it into a calculator, since this would typically also be a calculator problem. If it was not a calculator problem, then you might want to go the route of splitting it up, which is also ugly and takes a long time, but would be less difficult to deal with than this without a calculator. And when we toss that into a calculator, we get approximately 19.556. Okay. Any questions with that one? Okay. I'm going to grab one for you guys to do on your own, and then we'll move to the assignment for today. Let's find a decent one. Oh yeah, that's a good one. Okay. Not too time consuming here. We're going to go find the length of y equals 2/3 x to the 3/2 from x equals 0 to x equals 8. Okay, so go ahead and try that one. When you think you've got an answer, go ahead and type done in the chat. And this should be one that doesn't have any weird issues. All right, we got a couple people with answers. Awesome. Keep working on it if you don't have one yet. All right. Anyone want to share what they got for their answer? Yeah, I think that's what we end up with. Like 52/3 or something like that. Yep. Okay. Cool. So yeah, if you started off with something like this, if you were going through it by hand and everything, you'd end up with 1 plus x, which is 1 plus x to the 1/2, which is then 2/3 times 1 plus x all to the 3/2, evaluated from 0 to 8. Which is, if you plug in 8, you get 2/3 times 9 to the 3/2, minus 1 to the 3/2, 2/3. Which is 54/3 minus 2/3, which is 52/3 or 17.333 if you were asked for a decimal. The way we might see this one typically is as like a multiple choice problem on a non-calculator section. So you do want to recognize, still how to integrate something like this by hand. All right. Well, looks like most people made it through that problem, so that's good. Your homework for tonight. Let's get into that next. We got 2 things today. The first thing is the actual assignment for 8.1. Here it is. It's in the book, problems 3 through 5, and then 7 through 19 odd from 8.1 in the Stewart Calc book. And it's in Google Classroom as well. And so just like you uploaded the summer homework down here, you'll upload the assignment there as pictures or a PDF. If you're unable to upload things as pictures or PDFs or anything like that, let me know. We can work something else out in order to show your homework. So either stay after and talk about that or send me an email real quick and we can work that out. The other thing is another kind of get to know you deal, and it's going to involve the class banner. So it's a quick make a vanity plate or a personalized license plate that kind of represents you. Here's my example one. So you have at least 5 things about yourself. They can be pictures of things that you like or people that you like or things you like to do or shows you like. You need to have your name on it and then change the letters here to be something you might put on a vanity plate and then change the background as well. So that's an example. And there's the blank one for you guys to fill out. It should generate one for you. But yeah. All right. So that's everything for today. if you have questions or anything like that, feel free to stick around or pop back into the meeting. If you leave it, I'll be here for the rest of the period. So if you run into a homework problem and need a hint or something, let me know. Also, feel free to work together, especially with calculus. Working together is way more fun. So feel free to bounce ideas off each other via email or a Google Meet or anything like that you guys want to set up. Or if you need help setting up something like that, like working together time, let me know. I can do that too. All right. Unless anyone has any questions, you guys are free to go and start working.